Um, Welcome again. And Harry was commenting to me during before the previous talk about how many FLNG talks there have been. I mean, we had a whole session yesterday. I think this is the last one, so if you're not into FLNGs, you're almost at the end of the road. Um, Also, my uh, picture here doesn't quite match up with Mr. Kim's before, but this is an example of an FLNG that we're going to talk about today. So well, much of my first few slides are going to be a very short summary of what you just heard. But kind of have to introduce the FLNG, what it is, um, why we do risk studies and what type of risk studies, and then we will focus on cryogenic spill risk analysis. So, and we'll talk about CFD-based modeling and conclude the talk. So again, my images here don't quite, they're not quite as fancy as what you've just seen. But this is generally the arrangement of an FLNG. The whole advantage of this is to use stranded gas offshore. So you'll be pulling the gas into the FLNG, then you have a gas treatment area, and then you go, as the gas kind of flows from bow to stern, you go into, cooling and liquefaction, and then in this case we have a tandem offloading, or you can also have a side-by-side offloading. This is the Shell Prelude, the kind of the sort of one of the main examples of FLNGs, in production. There's going to be a lot more, as you saw in the previous presentation. This data shows many billions of dollars projected expenditure in FLNGs. So there's a lot of investment in there, and therefore there's a lot of interest in getting things done right. FLNGs present a lot of design challenges. The liquefaction technology is, fairly well established. It's not an easy technology, but it's been done for a number of years. However, now you're packing it into, a few football fields. That introduces inherent risks and complications. And then you put this on a floating vessel, and these fields, a lot of these fields are out in the middle of the ocean, so the environment can get pretty rough. So you have a lot of problems to deal with. So risk assessment is a big deal. You just heard a talk about fire and explosion risk analysis. We're going to talk about cryogenic spills, but either way, doing a risk assessment properly is critical to later on reduce potential downtime or catastrophic failures. The focus of the risk assessment here is purely on the vessel and the personnel. Okay? We're offshore. We're many, many miles away from any living person or structure. So there's really no issue with societal risk, or very little. I mean, maybe if you're near a shipping lane or something like that, but the focus is really on the vessel. And again, we just talked about or heard about the fire and explosion risk assessment. There we focus on flammable releases and consequences. So fires, jet fires primarily, or delayed ignition leading to overpressure. The idea there is to try and keep the damage to a minimum, and mostly, as you heard, the DAL, the design accidental load, the focus there is trying to prevent escalation risks, because that's what can take down the entire facility. The cryogenic spill risk assessment looks at cryogenic releases. So they're not quite as dramatic. The videos and animation that I show are always, a lot less exciting than the ones my colleagues show where they blow things up. But they're still quite important. I mean, you can do a lot of damage if you have a cryogenic spill in an area that is not properly protected. And so again, the goal here is to figure out what do we need to protect, um, you know, what's a compromise, because obviously you could protect your entire FLNG against cryogenic releases. You probably never manage to get anybody to pay for it, but in principle it can be done. So the idea is really what is the most efficient um, and safe combination. Okay, so that's what we're trying to discuss here. I just had a couple of slides, sort of touching back on the fire and explosion risk analysis. These are borrowed from my colleague Scott Davis' presentation last year. So if you were here last year, you can take a quick snooze. But one of the things that we look at, as you heard briefly in the previous presentation, are safety gaps, for example. So we want to try and one of the ways to reduce explosion risks is to separate things. You heard in the Hyundai FLNG that their modules are about 15 meters apart. Real estate on an FLNG is extremely expensive, so you don't want to have too much open space. So it's critical to find out exactly what's the minimum that you can get away with, because it can have a big impact on the bottom line. So again, what we showed last year and what is typically done in these ERAs is a sensitivity study on the effects of different safety gaps. And again, I'm going very quickly here, but you can see that, for example, for large clouds that would cross between adjacent modules, you can get a significant effect on the overpressures, the design accidental loads, if you extend the distance between the modules. I mean, this is obvious. You don't need a PhD in CFD modeling to understand that, but where do you start spacing them so far apart that it doesn't become economically viable anymore? That's the critical question. Versus the cost of a blast wall or some other mitigation measures to keep the risks down. So back to the cryogenic part. Cryogenic spill risk assessments are risk assessments. So it's not rocket science. It's not different from other types of risk assessments. What you have to do is figure out what are the relevant streams. Unlike an ERA, you don't have to look at every flammable stream. You only care about the ones that are cryogenic. Okay, so usually like the front third or so of your vessel is not part of the equation. You can focus on the liquefaction area and storage area. You have to determine process conditions, inventories, possible release locations. You need to do your failure rate calculation for small, medium, and large releases, or whatever the methodology you choose is. You have to set the damage threshold criteria. Here we're not we're not looking at overpressures. We're not looking at ignition of this. We're looking at actually when it doesn't get ignited, when it stays cold. So typical examples are, temperatures in the order of -30 to -40 degrees C. When embrittlement becomes, possible for non-cryogenic steel. And then you have your scenarios. You do the consequence modeling. So you calculate how far, what areas are affected by the cryogenic damage. For each of the scenarios in your risk assessment, and then you put it all together. So you combine the consequences with the frequencies, and you get your risk curves or your probability of exceedance curves or FN curves, whatever it is. So typically, these analyses are done with analytical models. I'm listing fast here because it's probably the most commonly used tool, but not necessarily the only one. One of the problems that we run into when we do this is that these analytical tools don't account for the interaction of a release with the structures, equipment, and everything else. Blast walls, firewalls, decks, you name it. And there's a lot of that on an FLNG. I mean, it's pretty packed. So you see here, I should remember to use the mouse. You see here an example of the hazard distance for a release. And you see that it goes through a bunch of structures, vessels, and this is one module, this is the next module. It goes into the adjacent model as well. So you could get pretty large distances. If you have a large release, it will go pretty far, often into the next module. That could be a problem. For example, sometimes we have firewalls or blast walls between modules, so it's not exactly possible for a vapor release to go through a wall. So the solution to that is, that we see often applied, is to cap the hazard distances to a certain number. For example, it could be the length of the module or some other value. I've seen different values and different justifications used in several projects that I've reviewed. So, okay, that makes it more physical. You say, all right, it can't go into the next module if there's a wall in between. However, and so, I've seen this apply sort of blanket. You have a spreadsheet with your distances, and you just cap those distances to 10, 20 meters, whatever it is. However, if you do that, not all modules are enclosed. So what if the module is open? What if we have this? Again, using the mouse. Apparently nothing in between here, so this could actually go through. Or what if the module is open, but there's so much stuff in here that maybe it's difficult for this release to actually get out. They're all valid questions that you should try to answer, and you kind of need to make some evaluations there. So one way to avoid having to make these assumptions or decisions is to do the modeling with a tool that can actually account for these interactions, so with a CFD tool. So in that case, you go from this geometry to this geometry. Okay? In one case, you have to decide, okay, can these 40-meter distances actually happen or not? In the other case, well, the calculation tells you you don't have to make that choice. CFD has advantages, as I just mentioned. The results are undoubtedly more accurate. You let the model do the look at the interaction, let the model do what it needs to do, and the results are, as long as the model is properly validated and that the user is knowledgeable on how to run the simulations, the results are usually realistic. And that is important because it keeps you from having to make conservative decisions. Okay, if conservatism is good, we want to be safe. Too much of it is not good. Okay, more conservative is not always better. It gets to a point where you just can't build a thing, and that doesn't help anybody. CFD obviously has downsides. Main one is this stuff takes a longer time. We can run 100 or so simulations with an analytical tool, maybe in a few hours or a couple of days, depending on how much input we need to enter. It will take longer to do it with CFD. There's no question there. However, when you have a $30 billion facility that is going to take several years to build, well, maybe you can afford to spend an extra month or so, and a small fraction of that money to do it right. And the money you will potentially save in not having to plaster with cryogenic spill protection half of your FLNG is probably going to be well worth it. So how do we do a cryogenic spill risk assessment with CFD? Well, the first thing we need to do is start with an accurate geometry. The emphasis is on accurate. Here we have two modules. They're two identical modules, so they're just for comparison. This is what you would typically get from your CAD. Particularly early design phase. Your CAD model is going to be fairly limited. You'll have big structures, big vessels. You can run a study here, whether explosion risk analysis or cryogenic risk analysis. You will get some results. They're not going to be good results for you. They're not going to be useful because your facility, when it's done, it's going to look like this. It will have a lot more stuff in there. So you need to spend the time and do it right, or you risk finding out too late that you may have a problem or you may have to go and change something. This is a time-consuming effort. However, it's the same effort whether you do the explosion risk assessment, the cryogenic risk assessment, or both. You don't have to rebuild this every time. So, it's not as bad as it sounds, since, a lot of people already do use FLAX for the ERA. It's really already there for you. Then you have to run the CFD simulations. Usually, when people hear this, the response we get is this. So maybe instead of a step 2, we should have a step 1.5. We should sit down, before we pull our hair out, and think about, well, which simulations do we really need to run? Do we need to run, 1,000 simulations all with CFD, or can we get away with less than that? For example, if we have small releases, this is a 1 kilogram LNG vapor release from the piping here that runs along the edges of the module, and you see that the distance, at least this is a cryogenic hazard. Okay, this is not LFL. I mean, that's a little bit different. This is the minus 40 degrees C temperature envelope. It only goes a couple of meters, 2 to 3 meters. So chances that this is going to hit structures and be significantly distorted are probably not very high. So maybe these type of releases may not require detailed modeling. Larger releases, on the other hand, are going to go all over the place. So there, it's more important. This is a 10 kilogram per second release, which is still not enormous. And you see that, I mean, it looks nothing like the previous one. Okay, it's not a straight jet that goes to whatever distance. It hits all this stuff, and there's a lot of stuff in there, and it kind of goes everywhere. Another difference of this type of studies compared with the sort of onshore sighting type studies is that we're not looking at we can't draw a circle around this. Okay, we're doing a risk assessment here. We're looking at specific releases. The wind direction is very specific, especially for FLNGs, because they tend to swivel around the turret, so they line up. So the wind doesn't really change in all directions. The release directions are also somewhat limited. You don't have them in 360 degrees. So again, you need to be very careful with just drawing circles and making conservative assumptions. Take a step back. Large releases, however, in some cases, some of them could have very low probability. So even though they may be, they will be affected by the structure, maybe the contribution to risk may not be so high. So really, maybe the best way to look at it is to find the major risk drivers. We find the major risk drivers and we focus on those. That's likely the most efficient. No, thank you. Most efficient solution. One other point is know your model. There are problems in some cases. For example, we found that if you have a downward flashing release with fast, the rainout predicted is independent of the elevation of the release. This is non-physical. It can give you very wrong results. So here we have an example of an LNG release where fast was predicting 95% rainout because this was just a couple of degrees above saturation. When we ran it with flax, with two different elevations, we got in one case 53% rainout, in the other case 40% rainout. The liquid spill, and therefore the cryogenic protection area, is significantly different. Okay, so that can be a problem, and it can either overestimate or underestimate your hazards depending on what hazards you're considering. As a result of the different split of vapor versus liquid, your cloud is also going to be different. Again, this is not the LFL cloud or half LFL. This is the minus 40 degrees C, so this is the cryogenic impact area. Something else that you can do with CFD that you cannot do otherwise is look at mitigation. So here we can look at the temperature of the structure. So we can see exactly, how far on a deck or on a pipe or a vessel do we have temperatures that would require spill protection. So all things that can be critical. So to summarize, cryogenic spill risk assessment is a critical step in FLNGs. It's not talked about as much as explosion risk assessment, but no less important. And accurate modeling is, can have a significant impact on the bottom line, on how you design and how you protect your facility from hazards. Again, yes, risk assessments purely with CFD are not impossible, but they do take longer. So perhaps with some clever thinking, like if you know what you're doing, you know what you're looking for, you can find a combination that may actually, give a more efficient overall process. And with that, I'm done. We have